So, and I'm generally somewhere around here, so you can usually hear me talk. You can usually hear you guys talk as well, so if you talk in class, it will be recorded. It's only available to you guys, though. Okay, so having said all of that, welcome to Math Physics 5360. Those of you that have not met me, although I've talked via email, my name is David Hilton. We have not talked yet, but we'll talk soon. That's my office phone number. That is actually Teams on this thing. We don't actually have, if you notice, we don't actually have phones anymore. They just make it Microsoft Teams. So if you call me on that number, you're going to ring the Teams app on this. You can also download Teams yourself and send me text messages through all of that. Or there's the Discord channel that will continue to be operational as well. Either of those is fine if you prefer text. That's my email address. You're here, so presumably you know where the class is and when the class is because you're actually here. This will be Tuesday, Thursday in this room. There is a non-zero chance that they move us to another room because we are not filling the last 2 rows in all of this. I'm going to fight it because they will move us to a room that you will all be crammed in like sardines like they did to me last year. But that happens sometimes because they're working on spaces and they're going to see that we're not taking up all of the spaces here and they need it for something else. And then they're going to stick us in a closet somewhere. That happened last year. It's great.
A106.
105, yeah, those. Yeah.
Yeah.
Yes, yes. I tried to get a real room,
Thank you.
but they're going to catch me.
It was a valiant effort.
Yeah. Okay. My office hours are going to be roughly the same time block on Mondays and Wednesdays. Nominally, this is a small enough class. Set up a time. Come meet me. I will send it to you as well. You all have the Calendly link so you can see my calendar. That'll remain active through the semester. You can see my availability and sign up for a slot. As I said, I'll send it to you as well. They've all gotten it because I'm graduate program director as well. But you can actually see my calendar and sign up for a slot. That's the easiest way to do this. If you can make it to my office hours, fantastic. If you want to be on Zoom for my office hours or Teams or whatever, that's fine too. That all works. I do travel, although not an enormous amount, although ironically Thursday, we'll get into that. I do travel a bit, so sometimes it's going to have to be on Zoom because that's when I'm going to be available because I won't actually be here in Waco. So that'll happen sometimes. Anything that's official here, I'm either going to send you a Canvas message or to your Baylor email account. So you do sort of need to keep a rough idea and watch all of those as well. Typically I send Canvas messages, occasionally I'll send out Baylor email messages as well. But these are meant to be just an update. Hey, I'm going to move the homework. You got 2 more days on the homework. That happens a lot. I have a rough template for all of this, but depending upon your familiarity with certain subjects, things move around a little. So I need you to keep an eye on your email. I know that I have been told by my stepdaughter that's an old person technology. It's great, fantastic. I really, really love her sometimes. So I realize that not everybody likes you. I need you to do that. At least keep an eye on it. Textbook for this class is ARVKid. It's a stock textbook. I'm not going to give you problems saying do problem 5, chapter 6 out of ARVKid. They're all written in Canvas. I will not entirely be following the order that he has in that book or generally referring to it in class at all. Textbooks are ridiculously expensive. They're crazy. Buy this one if you want to. I think that the bookstore keeps calling it a required text. They won't let me make it optional. I change it to optional, then oops, they accidentally change it back to required because that's their profit model on things. So get the book if you want it. If you don't want to get it, I'm okay with that too. I intend for my lecture notes to be complete in terms of being enough of a resource for you to solve homework problems and tests. Get it if you would like, but keep the $150,000 that you can spend on that book for something else if you want to, because they're really ridiculous. I remember back when I was a kid, anyways, back when I was in undergrad and books being expensive, and if you look at the growth curve, it's just ridiculous what they've done in terms of book prices. Decent amount of the homework, you are going to want to check your work on a Mathematica or a MathCAD, that's fine. Checking your work, not doing it on one of those. You do not have Mathematica or MathCAD or anything like that on the preliminary exam, so you don't want to get too dependent upon all of those, but if you want to use stuff like that to check what you do, that's perfectly fine. There are some problems that I ask you to use a computer software package, so I have it configured right now for Python, MATLAB, or Mathematica to upload. If you have another preferred language, fantastic. I have zero problem with that, let me know. I need to make sure that I can interpret that, so like Java or Fortran if you're old, really. Like if you have another way that you do this stuff and it works and you want to use it, I'm fine with that. Just give me a little bit of heads up so that I can actually run your code and check your work. I've used a bunch of different languages, but those are the ones that most everybody has wanted to. So if you need to upload a computer code right now, they're only going to accept those pieces of software, like an NB or an M file or PY file or something like that, or a Jupyter Notebook from Python or something. That's all it's going to accept. So if you want to do something else, just talk to me. I'm fine with it, but I just need to make sure that I can run it and I can check your work on that. Arts and sciences, you need to be to 75% of the classes pass. I'm going to do that by eye. If you stop showing up to class, I'll start being annoying, but I'm not going to take a roll every single time. A, it's a small class, and B, you're grown-ups. Anyways, but I have to say that. So what are we doing here? Math. So this is not a, hey, he's going to derive all sorts of proofs and they're really pretty and I have no idea. This is a practical math class. This is, for those of you taking Jackson E&M, this is a survival strategy. How to get through the math of partial differential equations, ordinary differential equations, functions of a complex variable, and linear algebra. So there's a couple of proofs in the entire semester, but for the most part, this is a, here's what you need and here's how you use it class. We do not have, as a research area in physics, mathematical physics. So you are all taking this class because quantum mechanics, statistical mechanics, classical mechanics, and electricity and magnetism need this stuff. And I don't know why Jonathan's got you taking this, but I'm sure some of that applies there as well. Yeah, so this is, in my opinion, a service class to get you through everything else. And I've structured this class accordingly from all of that. So all of those topics pop up at various points in the first year of all of your physics classes. So that's sort of the content of this class. But this class is very much how to survive Jackson, how to survive Sakurai, how to survive all of your other classes. And so the problems here are going to be physics problems with just that little veneer of physics taken off of them and turned into a math problem. Homework is, in my opinion, where you learn in this class. So homework is a little bit different here, and it's also a little bit different than I've done it in previous years, so don't listen to people when you hear it. So when you go into Canvas, you'll have a few fewer tabs. This is the grown-up version of all of this. You go into Canvas, you'll see the ones with the green check marks on it. There's 9 homework problems right now for the first test. There's multiple parts to all of it. So you click on a question, you get something asking you to do stuff. You'll upload through here. So you send me electronic versions of them. I electronically grade them. I send them back to you. If you've made significant errors on the problem set, you have to fix it. You've got to get a 90% on homework. It's a huge part of your grade here. And this goes back to my idea that this class exists because you need it elsewhere. So if you can't do a problem, let's figure it out here. So if you submit a homework problem, you don't do it right, you'll get some comments back from me, I'll ship it back to you, you're gonna need to do it again. You need to keep doing it until you get it right. This can be 10 times, I'm fine with that. It doesn't hurt your grade at all. The thing is when you're done with this class, I need you to be able to do this stuff because I need you to be able to do this stuff in the other classes. So if there's an area in all of this where you're really struggling with something like this, there'll be 3 or 4 back and forths with all of this. It's perfectly fine if you get halfway through a problem set and submit it to me and say, I'm stuck here. Submit it to me, I'll send some comments back to you, come onto my office, that's fine. I don't want any of you getting out of here without being able to do all of those. You're not able to see most of those, especially the ones that say exam. You're not able to see them yet. I want you to be able to do all of these. If that takes 3 or 4 versions, okay. It's not gonna hurt your grade. I'm not gonna take off points every time you submit something. That's not the point of this class, okay? The point of this class is that you can do this stuff in the end. You're all walking in, I'm assuming, with parts of all of this. When you look at those first 9 questions, you're gonna look at a few of them and go, yeah, I can do this one, and just wipe it all off all at once. That's fine. You don't have to do them in that order. You've got to get them all done by the first test, but you can pick the order that you choose. So if you've seen something in an undergraduate class, know how to do it, and you want to knock that problem off first, go for it. Spend more time on the ones you need it. Get the ones that you know how to do done fast for your first couple problem sets. Be working on all of the other ones from all of that. Manage your time that way. I know that most of you had some sort of mathematical methods class as undergrads. This is going to be more advanced than all of that. I'm fine with all of that. What I need you to be is, I'll say this a couple of times, I need you to all be at the starting line by the end of this class. I need you to have all of that mathematical background so that Jackson E&M next semester is only miserable, versus impossible. Everyone okay with that? So submit, you get a good grade on all of it, you're done. If you're not, you're going to need to go through and make corrections, submit it back to me again, I'll grade it again. You still have errors, I'll send it back to you. We may go back 3 and 4 times on this. I'm fine with that. What I want is for you to be able to do these sorts of problems so that when we get to the physics classes that you have to take, you can focus on the physics not making sense versus the math and the physics not making sense. Is everyone okay with that? It's a little bit different. Okay, so the thing that I'm doing differently this year, and you can thank the third years, the second year, and the fourth years, the third years, and the second years for all of this, you're required to turn in 2 problems a week. I used to make it as you were available from all of this, and then everybody turned them in the last week that was available. And then, and for fun, complained on my teaching evaluations that it took me a long time to grade. That was fun. I get all of you times 9 problems all at once. Why can't you return them tomorrow? So you can all thank them for all of that, but you need to turn in 2 problems a week. You pick the order. So if you go into Canvas and you know how to solve problem 8 right now, solve problem 8 right now, turn it in. I probably won't have even covered it in class. I know some of you are walking in with some of this and some of you are not walking in with some of this. Pick the ones you can do first, knock them off, so that you can spend more time later in the semester on the ones that are new to you. So you get to pick the order for all 9 of them, and again, those will be available in the next section of the class and all of that, so you'll see more of these. But pick all of them, solve the ones that you can do, the ones that you can't do, wait till I cover it in class, come to me for help, whatever. You get to pick the order, but I need at least 2 a week. So not Monday, but the following Monday. Because Monday, like that would be, hey, you really kind of jerk. Not Monday. So you have a week. But is everyone okay with that? Pick the order you want to do it, but I need 2 a week. All right? And once you've submitted it the first time around, there may be a back and forth. That doesn't count. 2 new ones a week. Okay? Okay. You need to have that 90% to take the test. So that's why I don't want them all coming up into all of this. I see no reason for me to ask you a homework question, not get it right, ask you an exam question, also not get it right, and then have it pop up to you on the final and also not get it right. We're going to break that. So if you don't know how to do it on the homework, great, find me. Submit half a solution, I'll give you some help on it. Whatever it takes, get to the point where you can do all of these. Show it to me here and show it to me on the final. And then don't forget it by the time you take the physics class, please. Please don't forget it by the time you take the physics class, okay? So test-wise, tests are open book here. They will also be on Canvas. So when I give a test, there will be a week. So there's a window for it. Right now, it's roughly that week. It's a full week there to give it. It's a timed test. You open it up on Canvas, and you have 2 hours to take it. You pick the time that you want to take it. If you want me to be available to answer questions via email or in person, don't open it at 2 a.m. in the morning. I'm way too old to be open at that time of the day. I will not respond to text messages at 2 o'clock in the morning. So if you want me available to answer questions on all of this, do it sometime during working hours, but pick a time that you want to make it work. Because I know you all have different teaching schedules, TA responsibilities, so pick the time that works for you so that you've got that full chunk of time to take the test. And you'll open it up on Canvas just like you will with a homework set, but there'll be a 2-hour timer on it or a 3-hour timer on it or whatever from all of that. Okay?
Can we like
Scan it and send it back in.
Okay.
Inevitably, every semester, Canvas crashes at the wrong possible time. Fine, just email it to me. There's an upload button there. Murphy's Law kicks in right when you're trying to submit the test. Great, it's fine. Just email it to me as long as it's a reasonable chunk of time afterwards, 20 minutes or whatever. I'm fine with that. I really am. Please don't take advantage of all of that, but it will happen. So there are a bunch of camera phone apps that you can use to scan to a PDF. A lot of people use those. It's easy to do. Whatever works. If you do struggle with a way to do all of that, then find me. We'll find a way to make this work. So first chunk of the class is ordinary differential equations. That'll be 7 lectures. partial differential equations, complex variables. We'll have a week off for Thanksgiving, and then linear algebra. There's not a separate test for linear algebra. They'll just be on the final. The final will be given in the same way. There will be a little bit more restriction on is when you can take it. So when we get closer to all of that, we're gonna sit down with your other exam schedules and find a time window for you guys to take the final that doesn't make you take the final right when you're done taking Jerry Cleaver's final. And so we'll sort through all of that. And I wanted to leave it open because I don't know what your schedule is like. So we'll sit down and we'll find a block of time for you all to be able to take it on like one 24-hour window when you don't have 5 tests that day. Okay? So, as many of you are aware, Baylor is a religious institution. I'm Catholic. I don't schedule things around Catholic holidays and Christian holidays. If you are not, and you are of another faith, and want me to avoid certain dates for scheduling stuff, please find me. I'm happy to respect that. When I was at the University of Rochester as an undergrad, there was an unofficial rule that you just didn't schedule stuff during Yom Kippur and Rosh Hashanah because there was just too many students there that celebrated. So if there's particular dates that you would like me to avoid having tests due, stuff like that, please find me. I'm happy to make accommodations for all of that. Academic integrity. Okay, so this class is meant to help you in your other classes. So if you cheat in my class, it kind of annoys the crap out of me. I'm not gonna lie. Please don't. You have multiple attempts to submit the homework. So if you don't know how to do something, this is your opportunity to figure it out. This is your opportunity to have a back and forth with me, to work through all of those questions, figure out how to do all of this. I'm leaving the tests online to reduce the stress somewhat. You've got an available window. You can pick the time for all of that. They're open book, open notes. Please don't use ChatGPT to do them. I don't even know if ChatGPT can do this level of math, but please don't. Period. Please don't cheat. If you do cheat in this class, I'm going to be a jerk. I'm really going to be a jerk. This class is not independently important. This class is meant to help you in other classes. So I'm going to be really, really annoyed if somebody cheats in my class. And I'm really going to be kind of a jerk about it. Yes, sir.
I don't know what this would fall under, but say we did, like, we all took math methods as an undergraduate.
Yeah.
Say we notice, hey, this problem looks similar to something I did as an undergraduate. You still have the homework. Are you able to look at that, or is that kind of frowned upon?
You can look at your homework in this class. You can look at your notes in this class.
Okay.
But I prefer you not to. Yes.
Gotcha.
So. All right.
Thank you.
When it comes to my homework problems, I am perfectly fine with you all sitting in a room and asking what's he trying to solve. All sitting in a room talking about the problems. All sitting in the room on a dry erase marker board working through pieces of all of that, as long as everybody's solutions are unique. So if you can help each other learn, fantastic. I'm good with that. I have no problem with you working on problem sets together, not tests, but on the problem sets, sit down and work together. That's perfectly fine with me, as long as you're teaching each other things. You may know one problem, you don't know, you can teach, great. That's a lot easier. I took this class at the University of Rochester in, fall of 1997. How many negative years old were all of you? -4? Okay, great, thanks. I'm gonna cry now. So, what?
A couple months old.
A couple months old? Okay, stop making me cry. I'm still
I was
mad.
1.
What?
I was 1.
You were 1? Okay. Yeah. That was my master's year, and I took, you were 4? Okay. But, okay, so at least a few of you were around, so that, it's a couple of years, I'm really gonna have to start crying at that line. But, so I have been doing this stuff for most of your lifetimes. So it's easier for you to teach each other than it is for me to teach you. So I'm perfectly fine with you all working on the homework sets together, as long as the solutions are unique. So you're writing out your own solutions. It's fine if people work on the board together, but I need you to write your own solutions on everything, and then the tests are going to be your own work, not working together on that. I know other faculty have different opinions on all of that. That's mine, which is teach each other. Gang up on me. I don't make sense on something, you guys make sense, make fun of me for that. I'm fine with that. I'm totally good with that. Okay? As long as you can do the math by the end of the class. That's the goal. Okay. So homework is 30% of the grade. You're all going to get a 90 on it, at least. Possibly higher. Because we're going to keep going back and forth until you do. 3 exams, each 15%. Final exams, 25%. And yes, I can do math. There was actually one year I teaching a math class and that didn't add up. It was great. It was fantastic. It wasn't at all embarrassing that I couldn't do basic math. This is the official Baylor University turn numbers into letter grades. I'll stick with it. That's what I do. Questions? Everything should be in Canvas as we go through all of this, so you should be able to keep up on your grades for all of this. If you have need for accommodations, time and a half on tests, all of those sorts of things, that's how you go get them registered and bring that to me as soon as possible. I have done this in the past. I'm perfectly happy to configure your exam for time and a half if that's what they view as necessary for all of this. So if you have need for accommodations under the various federal laws, Foster Success Center, Sid Rich, it's not that far from here, get it registered there, get me the piece of paper on all of that, done. No questions asked. Okay. This is the new one this year, they're sticking in. They gave us 3 possible policies for artificial intelligence. Just don't use it. I don't know whether ChatGPT can even do this. Yes, sir?
For the homework sets, if we get above a 90 but not 100, can we still read through it for the
Sure.
extra notes?
Absolutely. Absolutely. That's fine. I just need you to get the vast majority of everything on all of this. Sir?
So if we don't get 90, we just keep resubmitting it?
Yep. Keep submitting it to that link. I will usually, typically what I'm doing on all of them, because I'm grading these a lot, I'll draw a line on your paper, like everything about here is fine, give you some hints beyond all of that. And then also, sometimes I'm told my hints don't make sense. They make perfect sense to me, but I'm told sometimes I don't make any sense. Find me. You can text me through Teams app, you can find me in my office, whatever, make it work. I try to give good feedback, but I've been told sometimes it's not, and it's fine, just find me. This is everything makes perfect sense to me. All right, artificial intelligence. Somehow I doubt any of these can actually do these sorts of problems, but please don't use any of that stuff. It short circuits the whole thing. The whole thing here is to go through the thought process. You will notice when I lecture, my notes are sitting there and I'm barely looking at them. It's keeping me on track, but I'm actually doing the problems here because then I have to explain to you how to do the problems. You've got to figure out how to do the problems and don't use any tools to short circuit that because that's the only way that it will stick in your brain. So this is just, I don't even know how that even works in this class, but please just don't use any of those. If you have questions, I'm probably slightly more understandable than ChatGPT, although only slightly, but I'm probably slightly better than that. Okay? So you've got my office hours. I want everybody in this class to get an A. There is no curve here. That is what is necessary to get an A. If every single one of you gets to that level, great. I am not trying to force a curve. I'm not trying to get one person an A and give everybody else, I'm not doing any of that. I am pinning myself down right now to what is necessary to get an A, and I will give one to every single one of you. If you get there, I'm fine with it. And then I'm giving you basically 30% of the grade towards that to start with. So I want everyone in here getting the knowledge out of this class you need to be good in your other classes. So if you are a first-generation college student, Baylor has a number of resources that are available to help you. You all know at least one first-generation college student. Me. Neither of my parents graduated college. I'm a statistical anomaly to go from that to doctorate in physics. I'm a statistical anomaly for a lot of reasons, but for that one as well. So first-generation college students, there's a number of resources here. If you are in the military, in the reserves, or in active duty, I will work around whatever you need. Just let me know. There's a number of resources on campus to support for all of that. This is a stressful major. You did not choose an easy doctorate in either physics or chemistry. You've sort of given it to yourself here. There's a number of resources that are available both on campus and nationwide. If you need help, you can also text me and call me. Let me know how I can help with that. Many of you are probably aware of Baylor's long and unfortunate history with gender-based discrimination and violence in Title IX. If you have not heard about the Title IX policy at Baylor, it's pretty detailed at this point. There's some history behind the football team taking advantage of some women about a decade ago. It was pretty horrific what was going on with that. Title IX is serious. It is something that protects people from discrimination for a number of protected classes, including there. If you think you are seeing something about all of that, there are resources that you can call. There's a Title IX coordinator, there's a phone number there. There's a web page that you can use to submit anonymously. If I think something is going on with all of this, I am a mandatory reporter. So if I think something is going on that's remotely Title IX related, I'm legally required to report it to the Title IX office. And even though I have tenure, if I don't do that, they'll fire me. And they're allowed to under Texas law. So this is something that's treated at Baylor and certainly in Texas very seriously. Treat everybody with respect. This is not an issue. If you are teaching assistants and looking in your labs and you see things that might fall under this policy, bring them to a faculty member if you want to, or you can make an independent Title IX report yourself. But this is something that is treated more seriously now than when I was in college, and that's a good thing. Okay. Questions? Concerns? Bad jokes? Those are mine, but you can add them in whenever you want. It's fine. Yeah. You guys are going to have to start being more animated or you're going to put me to sleep. Okay. So when you go into Canvas, I have programmed Canvas to serve you up the syllabus every single time. So don't tell me you haven't seen the syllabus, because every time you open Canvas, you're required to see the syllabus because I'm slapping you across the face with it. So it's there. If I make any changes during the semester, this timeline may switch. So if I make any changes to this, I'll highlight it in a different color, red usually, so that you can see things that might have changed, because this timeline will probably shift a little bit just in terms of things that you need me to go in more detail in or in less detail in, depending upon the background. So things might shift a little bit, but that's always going to be the first thing you see when you open Canvas. Slightly passive aggressive, yes. I'll admit to that, but I didn't know that was a policy. It's in the syllabus. Oh, I never read that. You guys suffer from all of the stuff that I've done. I started teaching in 2007. There's all sorts of stuff in this that I can tell you the story behind. So I apologize, but it's only slightly passive aggressive. Okay. Any questions? Okay. So for lecture, that's going to be on my iPad. I'm going to serve that to you I should have actually pointed that out to you. So under Files as a tab, under Pages, there's a link here. And so that's the link there you'll want to bookmark. That's the Dropbox folder where all of the video files are going to be put in, and the PDFs of all of my lecture notes are going to be put in. They'll be put in typically later in the day of the day that I lecture. If they're not, email me because I'm an idiot and I forgot to do it, which is entirely possible. That happens sometimes. But I try and get the video files up there as quickly as possible. And there's going to be, this is a PDF file and it's going to grow as the first 7 lectures go on, so I'll just keep talking and writing down the end of all of this as this goes on. When we're done with ordinary differential equations, I'll start a new notebook with PDEs, and then I'll start a new one with complex variables, and I'll start a new one with linear algebra, just so that we can keep the files all together, so that the document will continue to grow, and then it'll stop growing. And I'll mark it final when I'm done with it. And you'll see lecture 1, lecture 2, lecture 3, along with today's date on it. If I do anything where I am using the previous lecture because the recording didn't work, I'll highlight that for you, because it won't be exactly what you heard, but it'll be very similar. Even the bad jokes are probably the same. Every once in a while I'm telling a joke and I'm like, I've told this joke at this point in the lecture for the last 3 years. It's a good one. All right? Questions? So, there are 2 lectures that I used to give. They're going to be online versions of all of this. There's one technique that's called a method of successive integration. It's got a limited subset of uses. I do want you to see it, but I would rather spend more time on other topics. So I'm going to post just a video file of about 40 minutes for you to watch on all of that, and you have 1 homework problem on it. I don't want to completely eliminate it from the class because there are apparently some numerical techniques that build off of that particular integration technique, but I need to be able to do more with partial differential equations and complex variables. That's sort of the meat in terms of a lot of content you guys haven't seen before. So I want to spend more time on that. And then the other thing that I think this year, if I need to, I'm going to turn the one numerical methods class into an online lecture as well, when it just goes over the basic details of how a Runge-Kutta numerical solver works for an ODE. You have one problem on all of that in the homework. I'm going to try and do it in class, but I may decide that that's one that will be online as well. And there'll just be extra, hey, you've got all the free time in the world, just an extra lecture to listen to. Okay. All right, so let's roll. So what are we doing in this? So this first section and the next section, we're going to be looking at how to solve ordinary and then eventually partial differential equations that pop up in physics. So, and I'm going to give a little bit of a subset to all of that, which is we want to be talking about things like Schrödinger's equation. And I'm going to write beyond all of this, but I just wrote this stuff down to start with. After this, I write everything out. So it'll slow me down a little bit. But we want to talk about Schrödinger's equation, where I've got a second derivative plus a potential as an operator, and that's a linear operator. I'm going to talk about the wave equation, so that's a partial differential equation, but it's linear in the operator in x, and it's linear in the operator in time. So that's a multi-dimensional differential equation, but everything there is a linear operator. So I want to look at a set of linear operators here, either a derivative, a second derivative, a partial derivative, mixed, whatever, linear operators. What we're not going to be considering in this class, that pops up, happens in physics. My own field, nonlinear optics, the polarization is dependent upon the square of the field. So it pops up, you see this, but we're going to restrict ourselves to linear PDEs in this class. So no products of derivatives, no powers of derivatives, or anything like that. So everything here is going to be nice, simple, not really simple, but nice, straightforward linear operators here. So I'm talking Schrödinger diffusion equation, I'm talking the simple harmonic oscillator, I'm talking all of these things that pop up in every field in physics and chemistry. I'll say physics, I mean physics and chemistry, but you know what I mean. So this, lots of ways of doing all of that. We will not have time. So if you need to do nonlinear equations, we'll have to take a different class from all of that. But in keeping with this space here, we've got a lot to do in terms of solving these equations. So I want to start off with the straightforward, everyone's seen it, equation, which is a second order differential equation, and I want to do this with constant coefficients. So I'm going to be looking at, this is going to be an ordinary differential equation for right now. We'll do partial in the second half of this class. So everything here is going to be one-dimensional. So I've got a second derivative here. If you're writing this out, leave space. The first derivative, and then the function itself. And then this might equal 0 if it's homogeneous, or we'll consider something in general where I might have a driven differential equation. And I'm going to have, for right now, the simplest version of this would have 3 constants there. Obviously, a lot more complicated equations might have more things than just the constants. Let's deal with this first, and let's build from all of that. So this is a linear operator as I defined it. I've got simply the function, 0th derivative, it's first derivative, it's second derivative, there's no products of things here. This is inhomogeneous because I've got a forcing function here. And so we want to look at not just what you learned in differential equations with particular solutions. And if you remember differential equations, the solution strategy for this equation for a particular f of x is guess the right answer and prove that you guessed the right answer. And here's all of the strategies for figuring out how to guess the right answer. But that was the sort of generic solution strategy is, here's this one with this one, that's what you use for this. It was pattern matching. We need to go beyond all of that. We need to be able to do things here that are more complicated than what you saw in a differential equation. So this is the equation for a harmonic oscillator, right? So I have a simple harmonic oscillator, and we'll do this one, and I turn on a driving force that starts to shake it, and then I turn it off. So I've got something that's 0, I've got some sort of forcing function, and then it's turned off again. How many of you did that in an ordinary differential equation as an undergrad? How do you do it? Okay, so no one's gonna raise their hand from now on, because you know I'm gonna do that to you.
Set boundary conditions.
You can do it to a certain degree with some of them by doing that, but not in general.
Okay.
So, right? So that's a physics problem, right? People can do that. You've got, in spectroscopy, you've got, and that's what I do, you've got a light source that turns on, you vibrate a chemical bond, that's a simple harmonic oscillator, and then the light source moves on. I do pulsed spectroscopy all of the time. So I have a pulse that comes through for 100 femtoseconds, shakes stuff, and then goes away. How would I solve a simple harmonic oscillator if I wanted to consider that chemical bond as a simple harmonic oscillator? How would I solve that? Because I've got a driving force that's on and then back off again. That's where we want to go with all of this, and so I need to get to that point. So what's the solution strategy for all of this? Well, it's basically the same. So you start off with, you solve the homogeneous. So that's the full inhomogeneous equation. So the first thing you start to do is you find the homogeneous solution to all of this. And once you found the homogeneous solution to all of this, then in differential equations as an undergraduate, it was how do I guess the right solution for f of x? We're going to come up with something better than that. Multiple something's better than that. So physics-wise, I think it helps to put a picture on this. So I'm going to do a free body diagram, because you all loved them as undergrads. So I've got a block. It's supposed to be square. And put it down on this surface. And then I've got a spring with damping. And so this has a mass here. And I'm going to call this x equals 0. And so that's the equilibrium position for all of this. This is my x-axis. I'll make it easier. Take friction off that surface. I have damping on the spring, but I'll take friction off that surface. And so if I did my free body diagram, then I've got the weight down, the normal force up, the balance in this direction. I've got the restoring force for the spring, I've got the damping force for the spring, and then pulling it the other way. I'm going to get a differential equation that looks very much like that one in the top, where spring constant's k, twice gamma is b, and a is 1, or something like that. So I would get an equation that looks something like that, doing this simple harmonic oscillator and a mass on a spring. So that would be a problem like this that I would do in physics 1420. If I wanted to add a forcing function onto this and people would need to do differential equations, then that might be an undergraduate, junior, senior level mechanics class, something like that. You'll do a lot worse in Alan Farhan's class, a lot more complicated than that. We're adding complexity onto problems. We're not really adding new physics as you get into grad school. So I have this physics case here. And so I need to now come up with the solution to this equation. And I'll copy it down here first. So as a strategy, you always found the solution to the homogeneous equation, and then you added the particular solution onto things. So what's the solution to that equation in general? Exponential? Okay, what would I write down for that? That's correct. What do you want me to write down? So what should be my test solution for psi? You said it's an exponential. That's correct. What would I write down?
Well, I remember solving the auxiliary equation.
Mm-hmm.
So each of those linear operators turns into like, you call it some variable like m.
Mm-hmm.
And so like the second order derivative would be like n squared.
Right.
So you solve for like a squared.
That's right.
And those solutions would just go into exponent.
So I have some initial value here. I'm going to use S because I want to lead towards something, so I'm going to use S for what you're talking about. But so you start off with a trial solution there that looks like this. And going back to this physics problem, what can happen? Well, so I can have an oscillator. So I can have something that's a sine or a cosine oscillating back and forth. If I have damping there, then that amplitude is going to decrease in time, so it's going to be an exponential times a sine. And it's certainly possible, if the damping is massive, that the oscillation doesn't actually happen. It's just an overdamped system, and so it's just a decaying exponential. So this can handle the decaying exponentials part. Using Euler's formula can handle the oscillating part, so I can get e to the I omega t, or omega x, or whatever out of this. So taking a trial solution like this can handle the various physics that we know pops out of all of this, which is it's going to be a damped harmonic oscillator because of gamma, or it's going to be an overdamped system that just dies. One of those two things are going to happen from all of this. And obviously, under certain circumstances with these sorts of problems, you can just have a variety of different solutions to that. So, but if I take this as a trial solution, then I do exactly what you were talking about here, which is, if I do d psi, let me do that again because it looks more like a partial. And this is going to be s, and then psi 0 e to the sx, so that's just going to be psi of x for that. And then I could do the second derivative of all of this. And that would just be 2s's, s squared. And so then these can get plugged into this equation. And so I'm going to get a s squared. I'm going to gather the psi of x to the n, because it's going to be on all of these terms, plus bs from the first derivative, plus c, and then there was a common psi of x on all of them, and that equals 0. So I've got a couple choices here. It's that times that. So either of them could be 0 to make this work. So my first solution would be to say set that equal to 0. That's the solution where nothing moves. Is that a mathematical solution? Is that an interesting one? Probably not. So yes, that's a solution. You need to consider it. It might describe your problem, but you just did a lot of math to talk about something that doesn't move. You probably figured that out before now. So as solutions go, setting that equal to 0 is not a useful physics solution. It's a mathematical solution, but you probably didn't get this far to end up there. So your other solution would be to say what's in the square brackets equals 0. And that's what you were talking about. So now I have and how do I solve this? Hey, quadratic formula, isn't that fun? So I've got an s negative b plus or minus b squared minus 4ac over 2a. Okay. So this is going to give me two solutions, one for the plus sign, one for the minus sign, and it's going to give me two solutions that look like one of three things. Excuse me. Okay, so let me do this. I'm going to call these two numbers S1 and S2. Those are just the two different roots there. So it can be the case that S1 and S2 are both real. And that's going to happen when b squared is greater than 4ac. So that would mean this is a positive number here, so that when I take the square root, I'm going to get a positive number, and the whole thing here is going to be real. So it can be the case that these two things are both real, and I'm going to get a solution that just dies. That'll be my exponential e to the S1x and e to the S2x, where s is a real number. So that's going to be my overdamped solution in this harmonic oscillator. I can get a solution here where S1, excuse me, there's 4 solutions that I wanted to look at. Maybe there was something I was missing. This is why I should look at my notes a little bit more often. So if I turn off the damping, it could very well be the case that I get 2 solutions here that are both imaginary. If B is 0, then if A and C are both positive numbers, then I'm taking the square root of a negative number. And so if that square root is going to be I times a number. So I'm going to get an imaginary number for this, and I'm going to get the plus imaginary number and the negative imaginary number for this. That's the oscillator. It's just oscillating, and it's going to continue on forever because I turned the damping off. So whatever work I do in this system to get it moving goes nowhere because there's no damping. The energy is just in the system. It goes back and forth from kinetic to potential forever. So I'm allowed to do all of that as long as I make the problem completely not physical, because of course there's always going to be some sort of damping for whatever reason. But mathematically, I could have real solutions. That's the overdamped solution. I could have a pure oscillator. So the solutions here are just going to be sines and cosines. I can have a situation where B is not 0, and these are both complex numbers. Can't write today. And when you do this, it's just the imaginary part that flips sign because of that plus or minus, so they're actually complex conjugates of each other. So it's A plus IB and A minus IB, or something like that. And then the final situation here, and actually I need to give myself a little bit more room, is they could be the same number. And that's going to happen when B squared is 0. So they would be the same number, they just make negative B over 2A, but you get the double root for all of this. All 4 of those scenarios can occur from all of this. So first one, solution, excuse me. This is going to be they're both real numbers. They're either a growing exponential with x or a decaying exponential with x, depending upon the plus or minus sign of S1 and S2. That's your overdamped solution for this equation. If these are imaginary, then I'm going to make a slight change here. So these are still complex conjugates of each other. They're just imaginary parts. And so I'm going to put I omega for S1. It's an imaginary number, so I'm going to factor the I out and call the other part of it omega. And they're complex conjugates of each other. So the other one is minus I omega. It's just a slight shift in notation there. And so this solution here would become I should probably have used, let me change my notes because I annoyed myself last year. I'm going to call it K just because it's X, and I do optics too much to call it omega X. KX. Sorry about that. So I get sine waves and cosine waves, either the I kx or either minus I kx, either way. So I get oscillating solutions. If these are both complex numbers, then I'm going to do gamma plus IK, and S2 is going to be gamma minus ik. And so I would end up with solutions here that look like exponential times oscillating solution. Looks like that. And for this last one, they're both the same number. And it's a real number, so I'm just going to keep using S for this. Oops. Okay, so for the other one on all of this, it's the same root, so that's one solution. This is a second order differential equation, so there has to be two linearly independent solutions. And that's one of your homework problems, to figure this out. So you get to figure this one out. What's the other solution here in this degenerate case? And I'm going to pull back from your differential equations as an undergrad. The way that I did this is you use the Wronskian. If you've forgotten how to do that, come to my office. We'll go through it. But there's a second solution here, and you can use the first solution to find the second solution to all of this, in the case of degenerate roots. That should all be vaguely familiar. You've seen pieces of this before. You might not, in a physics class, you might not have seen it written quite like this. It would have been sines and cosines and those sorts of things. I want to keep the exponentials here because I want to build off of all of this. Okay, how am I doing on time? Oh, wow, still doing good on time. What did I forget to talk about on the syllabus? Anyways, sorry. I'm usually looking at this going, oh crap, I don't have enough time. Not, I have 20 minutes more. Weird. Okay, so why am I doing it this way? So I'm sticking with this as my trial solution here. And I'm able to, taking that mathematical form and resorting to complex numbers, I'm able to solve this particular solution using that generic form. And the question now becomes, what are the values of S that I need to solve my particular problem to get something that gives me the type of solution that I expect to see based on the physics that I know? So I have this trial solution here, and then I have a problem in that, how do I solve the particular solution now? So if the particular solution is a sine or a cosine, you're good. Because you already know that this solves it, so versions of the sine and the cosine can be turned into complex solutions, and you can find the amplitudes from all of that. If that's a bunch of exponentials, you're probably pretty good with that as well, because your inhomogeneous forcing term looks a lot like what the equation is serving you up to use. And so we're going to be using that language a lot. These equations hand you something to solve. They give you a preferred solution, an eigensolution, and you've got to build everything up out of all of that. This equation is giving you this. So if I happen to give you a forcing function that looks just like this, you're an undergraduate in differential equations. That's what they did to you. What I'm going to give you is stuff for forcing solutions that look nothing like this. And it's still correct, right? I can have a spring here where I shake it for 2 seconds and then I let it go. So I built up a certain amount of energy by doing work on it in 2 seconds and then I let it go. It's not kicking it by an impulse. It's not dragging it to initial conditions and letting it go. It's applying a driving force for a period of time and then turning it off again. This is me coming at a chemical bond, which is a harmonic oscillator, and hitting it with a light pulse for a short period of time, driving amount of energy into that, and then letting it ring out over time. So I want to be able to solve things. And so when you did this as an undergraduate, you largely got handed this. So, and by the way, it was hard. They were teaching you how to do all of this, so I'm not dissing all of that. But for particular solutions, if I want you to guess the right solution, I probably was giving you something that was an exponential or a sine or a cosine or some combination therein because it was straightforward to do. What we have to build up now is the mathematical framework to say, hey, I'm going to turn this on and turn it off and drive it, and it looks nothing like that because that goes on forever as an oscillator. So, but this linear operator is giving me this thing. So I need to figure out how to turn that, putting it through a linear operator, into a superposition of these things. And that concept pops up all of the time here. So I want to, and I'm taking my shoelaces out before I trip and fall. Let me fix my shoelaces. This concept pops up all of the time in this class, which is my linear operator, and in this case, L hat is that this linear operator under these circumstances have given me this function. So if I need to find something that's more complicated than this function, I need to consider that more complicated thing as the superposition of these. Let's do some examples on that. So if I gave you here for f of x so let's do example 1. I'm going to give you that one. And maybe it's off, and then at t equals 0, I turn it on. But that's just initial conditions that I can set that t equals 0 point, because I'm letting this go on forever. Right? This, if I just turn it on at t equals 0, and that's the only mathematical form that I've got, it's going on forever. So the solutions that you find only work when the source is on for the remainder of the life of the universe. Probably a little bit difficult to do experimentally. So we want to be able to figure out stuff that looks more like this. But for something like this, I could do excuse me, it's a minus. I could break it into that. And then so I could have part of my forcing function That's a terrible omega. And both of these, give me a second to pick this up. Look quite a bit like that. So I can turn that forcing function into something that looks a great deal like the homogeneous solution here. So I know if I come up with a particular solution that's some sort of exponential, I know how this operator is going to handle it. It's going to take an exponential, a complex exponential, and turn out a complex exponential, maybe with scaling and all of that type of stuff. But the equation is going to be perfectly happy sticking in a forcing term that looks like that first term, because that's what it wants to deal with. That's the homogeneous solution that pops out of this under any circumstance. So I'm going to be able to come up with a particular solution if that's the state space that I'm interested in. But now that's saying that my harmonic oscillator, I'm going to, at t equals 0, it's going to be at rest, and then I'm going to turn on some sort of harmonic time driving force, and I want to figure out how the system responds to all of that, but I can never turn it off again. So maybe that's not a terribly useful physics example. But I have the linearity of this. So this piece here, I could put that into this operator, and I'm going to get something out of it, take a derivative of it, I'm going to get some factors down, but I'm going to get complex exponential again, take another derivative of it, I'm going to get some factors down, I'm going to get complex exponential again. So I can figure out the amplitude part of all of this based on that, because this operator wants to use that. So Let's do a different forcing function now. I'm just going to have to draw this one. That's supposed to be a top hat. Ignore the fact that I can't draw. There's a little that maybe I'll fix that later on. So this is something where I'm hitting this with a forcing function, and it's off. And then I'm putting a constant force on all of this for a period of time, and then it's off again. Or I'll make it more complicated than that. I can do this, but then there's going to be a driving oscillation, maybe at the driving the natural resonant frequency of the circuit, maybe not. Maybe I'm doing something completely different. And so I'm going to hit this with some sort of oscillation and then turn it back off again. How do I handle that? Does this look like that? Directly? No. But the correct answer to that is yes, I will find a way to make that look like this. Because, and this idea is going to keep popping up, that's what the linear operator wants you to do. This specific operator gives me this, so everything is a superposition of this. It's a linear operator, so if I have this solution, I can have a second solution that looks like this, add them up together. That's also a solution because this is a linear operator. Because we're not dealing in any of this nonsense right now. I got to be able to do this. I can't do any of these right now because the nonlinearity is going to kill me. But for this operator, the functions that come out of solving this operator are these complex exponentials, so everything is a superposition of them. Is that idea okay? You're going to get really, really sick of that idea in this class. Hopefully not too sick. So what do I want to do? For something like this, I have to consider this f of x has to be that. So somehow I need to make the thing that my operator wants to give me look like the thing that I'm driving it from. And I'm going to exploit the linearity of the operator to do that. So I'm going to rename this amplitude here. Capital F. It's going to be different for different values of S. So I'm going to have something that looks like that. As a matter of notation, I'm going to use a tilde on this F. And when I do that in this class, capital F here is typically going to be a complex number. And I'm trying to tell you that with a tilde. So when I do these transform pairs, there'll be F without a tilde, and then a capitalized F with a tilde on it. And I'm just trying to give you a little bit of a heads up. This is probably a complex number in most cases. So that's why I'm doing that. Oops, helpful if it was the pen. So I have one of these for one value of S, and that's this piece here, but I'm going to need to use superposition to add them all up to make it look like something here that looks nothing like an exponential or a damped exponential, or even that solution I didn't tell you was nothing like that. So I'm going to need to do superposition here. So depending upon the function, this is either a discrete sum or an integral. I'm going to write this as an integral for right now. There are cases where the f of x is periodic, where this will turn into a discrete sum. That's the difference between a Fourier transform and a Fourier series for those of you that have done this. This is not Fourier, this is Laplace. So I'm going to need to add these all up. So I'm going to do an integral now. Oops, again with the pen. So for every value of s, I get a certain amount of that contributes to my forcing function. And this forcing function is now a linear superposition weighted by a complex amplitude of the thing that the operator wants me to deal with. Is everyone okay with that still? I hope you've left space because there's a bunch of stuff missing. Is the idea okay? Equation gives you lemons, that's your lemonade. That's all you can do. And this all comes down to a practical thing. The operator gave me this. Everything has to be built up out of this. Okay, few things. There is a complex amplitude that's missing in front of all of this, and we will not be deriving that this time. Just for fun. And the limits of integration here are complicated, and we're not going to deal with them. So we're going to do, so this is the inverse Laplace transform. All I am saying there is I have a bunch of these. They all interfere and create my function from that interference. You've done this before in the wave equation. You've taken a bunch of sine waves and interfered them together to get some sort of complex pattern from all of this. Why did you use sine and cosine for that? Because that's what the wave equation handed you to. A spectrum analyzer exists to break light down into its individual frequencies because Maxwell's equations beats you upside the back of the head and says this is what you're using. Maxwell's equations give you that, so you're building light up out of sines and cosines, and there's frequencies, and there's different colors, and all of that type of stuff is a direct consequence of the fact that the wave equation gives you sines and cosines, and whatever more complicated phenomena you have has to be built up out of all of that. That's a Fourier transform. This is a little different because this is more electrical engineering circuits analysis. Fourier transforms and Laplace transforms are related to each other. They're related. We'll go through all of that. This is a Laplace transform because I picked a harmonic oscillator. I did a mass on a spring. I could have done an RLC circuit. This is all double E. They would have called it J versus I, and we're not doing any of that nonsense in this class. But the Laplace transform comes from the fact that the harmonic oscillator equation gives you this, so everything has to be a linear superposition of this. Because I'm restricting us to linear equations, and because this specific operator gives me this, everything is a solution of that. When it's Laplace's equation, and Laplace's equation gives you Legendre polynomials, you build everything up out of Legendre polynomials. When the wave equation gives you sines and cosines, there you go. When Schrödinger's equation gives you the spherical harmonics, you build everything up in the atom out of spherical harmonics. Whatever the equation gives you as its favorite solution, you exploit linearity after that to make more complicated scenarios. That's a Laplace transform, that's a Fourier transform. There's all of this math that gets built up out of that. Again, restricting ourselves in this class to something that is linear, because I can't say any of that for the rest of these. That's the fun part. But there's a lot that we can do in physics with linear differential equations. They're fairly useful. Questions? Okay, this integral we will not be doing until we get into complex variables. This requires contour integrals. This is what's called Bromwich's integral. We will do all of this for the inverse Laplace transform. The Laplace transform is the reverse of all of this. And so for a Laplace transform, I'm going to throw this down for now. And this will be probably Halloween-ish when we get to this. This is a solvable integral. How many of you have done complex variables before and done contour integrations? Okay, so you have to do a contour, and the contour is parallel to the imaginary axis, shifted off from the imaginary axis in a straight contour, and then you have to figure out how to close either the left-handed space or the right-handed space so that you can use the complex variables and all of that sort of technique to do this, use it as a closed contour integral. All of that's coming eventually. We'll do that example in class because that's a fun one. So when I ask you to do these right now, the problem is either intentionally going to end with calculate the Laplace transform of this, don't invert it, or it's one of a couple of them where the Laplace transform is easily invertible. So we will get into more complicated Laplace transform inversions when we get to contour integrals. The inverse operation for this to calculate the Laplace transform. And so typically, this is written with a script L. I'm writing this with a variable of x. If I was dealing with a RLC circuit, I'm looking at currents as a function of time, so x's would be t's. In that case, it'd be all the same thing. I'm just doing this with a position function right now. And this integral, this one is at least real valued. So this one is at least something that's doable. Excuse me. I always do that. This is always defined in terms of a half space from 0 to infinity. It's different than the Fourier transform. And it's defined in this way. So here, move it down a little bit, because this one needs a box. Okay, so a few things. I deal with, I'm an optics guy, I deal with Fourier transforms a lot more. Fourier transforms are notoriously incompatibly defined. There's pluses and minus signs, there's scaling factors that are different. In some cases, you've got a minus sign here and a plus one there in this book versus in another book, it's flipped. They're notoriously tricky to open up a brand new book, see Fourier transforms. You've got to look back at the definition to figure out how they defined it, because there's going to be these pluses and minus signs that float around wrong. And it's important to keep an eye on all of that, because if you define the Fourier transform with one harmonic time dependence and you use it on the other one, you're going to start creating energy out of nothing. Because in materials, loss for one harmonic time dependence is gain for the other one, and so energy won't be conserved. That would be bad. As physics rules go, that's really bad. So you need to be really careful with Fourier transforms, because as physicists, no one has managed to kill enough people in the other camp to establish one definition of the Fourier transform. So there's all of these sign conventions. Laplace transformed, the electrical engineers make whatever jokes you want about them. They have their act together. This is the definition of it. There's not these incompatibly defined dumb sign conventions from all of this. This is always defined with this in the minus sign, and that and a plus sign in front of S. They've actually got their act together with all of this. So this one's a little bit easier in that there's one definition. You don't have to be quite as careful about all of this. They will call it J, which is really dumb, but Gij, it's dumb. It's not the imaginary unit. That's not how the language works. Anyways, may have an issue with that. So at least with a Laplace transform, there's a consistency in the definition that's lacking in the Fourier transforms. Let me say one sentence, then I will be quiet, I promise. Okay, so what have I got here now? Let me go back to the beginning problem here, and what I said was the issue I wanted to deal with, which was that driving force, and not being restricted to that driving force looking just like the equation wants it. Anything here now is the superposition of these sorts of functions, the Laplace transform. We'll pick this up next lecture.